So the purpose of my talk is basically walk you through a process that we have gone through in the last couple of years. And in particular, I want to start with, I want to start with last year's presentation that was given by Mark Bunning, where he said, okay, if you would really like to accomplish something big, you better do things from start to end, involve a big team, and try to do something small. And what he was implicitly referring to is actually a project that was back then ongoing with Aramco. So I want to walk you through what happened over there. So what we wish to do is basically run through the entire innovation funnel with this, with the project that I'll be discussing throughout this talk, from ideation to prototyping and scaling it up. Most importantly, integrating it with our own geophysical workflow, testing it on complex, realistic data, and finally implementing that within the company. So as it is right now, there are colleagues of ours, geophysicists back in Saudi Arabia, who are implementing integrating that software with our geophysical libraries. And now there's, for the first time, a flag that an end user could pick, classical or quantum, for the kind of solver that they would like to do. So I think that's pretty nice. This, of course, involves, again, a lot of people. And at the beginning, you also need to involve people, people such as Frank, who will be giving a presentation later on, to give you a lot of hints on how to get started. But I want to first start by giving you a bit of an overview of, what is it that we do and what kind of problems are we solving. So I'm a quantum physicist, a theoretical physicist by background, who became a geophysicist 10 years ago. And those two paths kind of came back together about 5 years ago when we started looking at applications of quantum computing in this field. So geophysics is anything from very global aspects to understanding magnetic or gravitational fields and their variations on the surface. And we've seen talks on this already at this conference. Volcanics or tragic consequences of earthquakes, where we can understand more about them. Also, little known fact, when you look at the map of, or the skyline of Manhattan, there's a very good reason, and it can be traced back to near surface geology, why you'll be putting tall buildings on one side of the island and not somewhere else. And it simply has to do with, it's an answer that could be, it's a question that could be answered by means of geophysics. Archaeological excavations, understanding where critical infrastructure is under your feet, or understanding structural integrity of civil engineering projects such as bridges, that falls into this wider category. But what's particularly important to our company is energy and resources. So from conventional oil and gas to geothermal as well, benefits from what I'm going to tell you today. Understanding increasingly scarce water resources that we have to pay attention to, all the way down to mining. And the thing that we do effectively is taking an ultrasonogram, but on steroids. What we do is we involve massive boats with kilometers worth of cables towed behind them. You can see a helicopter pad, and the more recent ones, the bigger ones, actually have 2 of those these days. Through airborne surveys, land, and also, as of recently, doing this on other planets, which makes it the ultimate reason to work from home for a geophysicist. The seismic experiment is seemingly simple, but by the time it goes to scale, it actually becomes quite difficult. Because what happens is that you send waves into the subsurface. Every time the type of rock under your feet, its physical properties change, the wave will bounce back. And that gets recorded as like those little wavy patterns, little pulses of sound that come back to the surface and are being captured by those geophones. That process from capturing the data through processing it, imaging, and interpreting could take many, many months. It's not unusual that a project could be between 6 to 12 months of data processing, and easily involves petabytes, and at some points could swell to tens of petabytes of data. And by the time we abstract away all those things as we're solving this complex inverse problem, we're going down to sort of like an area of gigabytes for what the map of the subsurface looks like. So it's an incredibly data-heavy process, and a lot of the advancements that we see in our field actually come from that interplay of combining high-performance computing and then figuring out clever ways of building our software such that it can feed those massive amounts of algorithms into custom-built computational hardware. And the overlap of those three is really where the progress tends to happen the most. This is also what makes seismic imaging one of the most one of the biggest use cases for high-performance computing globally, and in particular when you're looking at seismic and reservoir simulations. So much so that we actually have our very own conference dedicated to this topic alone, so that QR code will take you to a place where you can submit your abstract, because as of last year, and we want to continue this tradition this year as well, we have a dedicated session to applications of quantum computing in the energy business. So the big question is basically what happens to this overlap when we make it quantum, and what can you do with current devices? And that's actually an extremely difficult puzzle to crack, in particular if you want to do something relevant and if you want to do it at the scale which is business relevant. So we're not going to be talking about some small little test or a POC. We're really going for the from start to end over here. And at the beginning, we consulted with our friends from TU Delft, TNO, Quantum Applications Lab, or the bigger Quantum Delta NL ecosystem to think of what's the best fit. And of all of those stages in seismic data processing that are involved, some are more or less difficult, some are optimization problems, some are just direct calculations. We've been able to identify one of them which actually is relatively difficult yet simple enough to convert to something that could be run on a quantum computer. At the same time, it could be relatively small and still remain difficult and relevant, and I'm not actually talking about just build the entire near-surface model building, but actually we'll be talking about one particular subroutine, which is the bottleneck of that calculation. So why near-surface? You might probably find it a little bit hard to believe, but in the Middle East, there's actually a lot of water movement underneath the surface, which tends to create karsts, or you can think of them as caves, places where basically sediments or other rock gets washed out from. And here's a picture of one where you can see that from the surface, you wouldn't be able to tell that there's basically an entire system of caves underneath your feet. And this is exactly not only what we would like to sort of detect or understand with seismic imaging, but actually because those features are below resolution limit, it makes it very, very difficult, and we have to detect them, and we have to use indirect methods to find them, because twofold: A, you do not wish to drill into those because you might risk not being able to recover your equipment, and secondly, they actually have an impact on your seismic image and the data that you collect. So this is your typical seismic data. You should be looking for shapes that look like hyperbolas. Hopefully, maybe you can see them. But the reason why it's actually more difficult to spot them compared to that image is because the difference between those two pictures is exactly the impact that those karsts would have on the data as it travels through those anomalies. And the reason is quite simple, because the waves travel through rock at about 2,000 to 4,000 meters per second, while through pockets of air they would go at 300. So it takes part of the wavefront and delays it relative to the rest and creates this jittery effect. And the problem with that is, if you look at here on the right on the seismic image, and if you pay attention to where the arrows are, in principle, what you're looking for is continuous stripes, slightly undulating, of white and black. Can you guys kind of see the white and black stripes going from left to right? How about now? Suddenly the image improved a little bit, right? Suddenly you could tell that some things came to focus with and without that correction. And that could have a very nonlinear and compounding effect on your entire seismic data processing flow. So for understanding data acquisition on land, correcting those shifts is very, very important. And the nice thing about it, what's particularly relevant about these applications, is that the advantage of the difference between a global and a local optimum could be as much as a difference between getting the image right and not. So going on to what we did around, so how did we formulate it in a quantum fashion? There is a mathematical formula which basically means that, or rather an assumption, that if you take every single signal that you measure after a couple of transformations, you want to make sure that they are nicely aligned. The transformation is correction for this overall hyperbolic shape. And you want to make sure that you align those signals relative to each other, and that makes it a nice combinatorial optimization problem. Nice for somebody who wishes to do a quantum computing and find advantage in it. Otherwise, not very nice at all. So what we did is we converted that into a graph problem, where for every vertex we basically assign one particular signal, and for every edge you would map across correlations between those two signals, subject to some relative shift between them. And the objective function of that problem, just for three traces with two relative shifts between them, is what you see here behind me. And the nature of it has to do with the fact that the signal that we're measuring is very, very oscillatory. So if you shift them relative to each other by just one period of that oscillation, it's still a good match. So you're basically littered with a lot of local optima, and what you really want is just a global one. The problem with this formulation relative to what you would find in a quantum computer is that this is a discrete optimization problem. And you have to figure out a way to encode it onto qubits, which only would take values of 0s and 1. So that's where the prototype came in. And we would break this process down into several steps that I will go over with you shortly. So first we needed to encode all of those discrete shifts into qubits, and anyone with just a single class in computer science would just tell you, okay, why don't you just binary encode that and be done with it. Problem is that this does not make for a quantum native formulation, and it sort of, you can't really do good quantum computing with it. Alternatively, those that do quantum annealing would tell you, okay, one hot is a way to go. Of course, the problem with it is that you have to use constraints to discount a lot of invalid configurations which physically make no sense in the context of your problem. Regardless, we proceeded with the one hot, and we realized that we could kind of get traces to somewhat align, but we very quickly realized that a lot of the time we are violating the constraints. Most of the time, the output from a quantum computer was dominated by constraint violators here in red, and very rarely we would get a result that actually makes any sense. So that was a little bit of a no-go, and the big challenge behind this is that from the search space, every time we were running a quantum computer, we were basically throwing away 99 or more % of all the possible configurations. We were not using a quantum computer efficiently at all. And we figured that the best way to do it is to hybridize the method. So when we did that, we went from 10 measurements to a whole lot more. I'm not going to go into great details of it, but we used something called binary partitioning, where we iteratively chose any of the two possible shifts, and we assigned that to a qubit, and we iterated. We looked at just the neighborhood so like a large neighborhood, we would look for a global optimum, and that allowed us to look at 2 to the power of 170, so 10 with about 53 zeros behind it, possible configurations at any single point in time. We would find a solution that we like, and we would around that build a new neighborhood and hop through this entire search space like that. Within a handful of iterations, we would converge to something that we would find satisfactory. The challenge with that, however, is that we spent a lot of time sending information from our local computer to a quantum computer, and 98% of the time gets spent on the internet. That slows things down considerably. But what this allowed us to do is to go to about 170 measurements at the time, which puts us roughly in the ballpark of what you would do in practice, because the practice is like anywhere between 100 to 600 signals. Then we decided that we have gone about this also we've made some assumptions which we needed to relax. I will not go into this part because it's not covered by what the company would like me to disclose. But the basic idea is that we have taken our search space and we figured ways of refining it. And as a result, we've been able to go beyond 200 signals at the time, and we picked up another factor of 2. And then finally, the one thing that we needed to address is figure out how we would actually communicate with a quantum computer somewhere far away sufficiently efficiently, because we signed up for a big package of quantum computer time, and we realized that we could only use 10% of it if we start on the first, and that stopped sending things to the quantum computer by the end of the month. So what we did then is parallelize the submission. So we would stagger all of the submissions relative to each other, and we basically kept the QPU preoccupied, picking up an effective factor of 20 on this computation. That process made it on par with a classical optimizer that we were running locally to get the same quality of solution. So next step was to integrate it with our software. So all we needed to do is, well, maybe I should explain that seismic data processing is a rather delicate process. You have to just pay attention where geographically a particular bit of data came from, and we're talking about petabytes thereof. So you have to integrate things with your database, apply particular kinds of pre-processing aspects, so those transformations. Those transformations actually depend a little bit on your knowledge of the subsurface already, so you have to link it to a different database. And finally, you collect those signals, which we would like to optimize with a classical solver, and those signals that I'll later on show you alignments thereof, because you can probably tell that we don't have any flat lines over here in the middle. A collection of those, tens of thousands of those, get inverted into a map of a subsurface. So what we did is we replaced that middle part with a quantum computer, and that's what we call the quantum annealer. So then we go down to just performing tests, and we have taken a purpose-built synthetic model of that. It's a data set that is about 0.5 terabyte, and it realistically models the subsurface that we are dealing with. Or at least models very well the problems thereof. So the orange patch of about 4 square kilometers was about 1 gigabyte of data, and we fed it through our algorithm and bounced it off back and forth of the quantum computer. And that's where the problem involved at most 75 variables, and then we pushed it towards in a direction of 200 with this much larger area, which also consisted of many more traces. So that's 10 gigs, and what you see behind me, because we have a model, is a ground truth of where those anomalies would be found, and now we can see the results that we got from our method. On the left, we see the classical. In the middle is the quantum approach, and the cool thing about it is that when we did this test on this particular data set, we managed to reduce it by a factor of the amount of computer time that we use and pay by about a factor of 10 relative to what the vendor would provide us with. Our goal is to reduce that by another factor of 10, which I believe should be feasible this year, which would start to look like something that we can gently whisper, okay, we're getting faster. This is an example of what this stuff looks like. So this is your input to quantum to the method as a whole. And in the bottom right, you see a number 0.0, which roughly indicates the quality of alignment. When we apply the classical solver on it, we bumped it by about 50%. And when we applied our method assisted with a quantum computer, we picked up another 15% solution quality on top of that. So this was an extremely promising result, and then you take that and you repeat that thousands of times with hundreds of thousands of calls to a quantum computer, and of course you're gonna get an odd result or two that don't work too well, which explains why this area here in the top left corner wasn't really resolved very well with the method. Probably a matter of configuring it, but when you start doing those things at scale, you can't just redo this every single day and retest it. So on average, on the small result, we got a 3% improvement. So these are basically histograms of relative improvements. So anything with bigger area on the histogram to the right basically means quantum computer assisted approach 1. On this very big data set that you see with 6,000 samples, roughly being just moderately better, but this gave us a 7% improvement, and some of those were even better than that. this was us running through this entire flow, but this is far from where we stopped, because well, now we have the developers release, so we're going to hear what our end users think of it. We would like to further look at squeezing the cost and time. The important step of it will be understanding and identifying only this kind of problems where we can characterize a data set that actually merits using a quantum computer and otherwise using a classical solver instead. We really wish to crack a 1 terabyte border this year, and I think we are just about to get there. We have other use cases. We're also looking at applying this on a Rydberg blockade. There's some people in the room that are helping us with this. And with that, I'd like to thank you guys for your attention.
Thank you so much. We have time for one little question, burning question.
Thank you for this presentation. A very quick question. You mentioned the 2 to 5 minutes time. What is the percentage of the QPU in this?
Oh, okay, so that is 2 to 5 minutes of QPU time. Okay. So this is not total time. The total time to perform this on a classical computer with like a deterministic easy solver is about an hour, but these are not very accurate. Global solvers would use about 10 hours, and now we are having our own classical solver with the call to the quantum computer, which is about a 9 hour classical, 1 hour quantum split, which time to solution is about the same.